Okay, in this video we're going to look at a classic position velocity problem. Here is the equation that describes the height of an object that is falling from the sky. Maybe somebody threw it off a cliff or something or dropped it out of a tree. Y stands for the height of the object in feet. X stands for time in seconds. And we're really interested in a couple of things in this problem. We're interested in average velocity and instantaneous velocity. Well, let's start with average velocity. If I want to know, on average, how fast is this thing going? What's its average speed over the course of from 1 second to 2 seconds? How fast on average was it falling? Well, I would need to know the change in the distance. I'll put change in distance, and I would divide that by the change in time. Now this should make sense to you. If you went 100 miles and it took you 2 hours to do that, 100 divided by 2 is 50 miles per hour, so that would be your average rate of change. Well, I'm looking for the change in distance over the change in time. So let's get a visual of what's going on here. This parabola represents the height of the falling object. Okay, I don't know if you can see this 100 up here, but this is where the object starts, and as time goes on, you can see the object is falling. It's falling to the ground at a faster and faster rate. Okay, so what I've done down here is I have these two yellow circles that I can put anywhere I want. I'm going to put the C value at 1 second. Okay, and we have some rounding error going on. If I actually plugged in 1 in for my time value, I would get back 84 feet instead of 83.84 feet. So there's some rounding error occurring here. But basically, at 1 second, the height of this object is right around 84 feet. At time equals 2 seconds, the height of my object is, this says 35.7 feet, but we know that if we plugged it in, if we plugged 2 in for here, we would actually get back 36. So what is the change in distance? Well, the change in distance is going to be the position of your final object, and I'm going to subtract from that the position of the initial object. So final position minus starting position. Let's go ahead and do that. Well, the final position of my object was f of 2. And the starting position of my object was f of 1. Okay, so this is my change in distance. Now, we already knew what those calculations were. We know that at 2 seconds that my object was at 36 feet. And we're going to subtract from that the initial height at 1 second, which was 84 feet. Okay, we need to divide by the change in time. Well, what is the change in time? How much time elapsed from 1 to 2 seconds? Well, that's going to be the final time, which is 2 seconds, minus the initial time, which is just 1. And if we subtract 36 minus 84, we should get, what is that? We should get negative 48 feet per second. And I have that calculation right here. Again, getting some rounding error due to the fact that this is probably something like 2.001 out here or something. I don't know. Okay, so we conclude that the average speed is negative 48 feet per second. Now the negative actually tells us something here. The negative simply means that this object is falling. Okay, so negative 48 feet per second is the average speed over the time interval from 1 second to 2 seconds. Well, what if we get closer? What if we shorten up that time interval from 1 to 1.5 seconds? Well, we can see on the graph here that if I shorten up the time interval and I take x to 1.5, okay, there I am right there, 1.5. If I plug 1.5 into this function here, I should get back 64, and it turns out that I do. I don't have any rounding error going on here. Looks like I still might have some rounding error occurring up here, but that's probably due to this figure right here. So we're going to do the same thing, the change in distance divided by the change in time. And it's always final minus initial, just keep that in mind. That's going to be important to make sure that you have the appropriate sign, whether it's a positive velocity or a negative velocity. Okay, so the average velocity then would be f of 1.5 minus f of 1. This represents my change in distance, and I'm going to divide by the change in time, which is 1.5 minus 1. Okay, so this should equal 64 minus 84 all over 0.5. And let's see, up top I get 64 minus 84 is negative 20. And negative 20 divided by 0.5 is negative 40 feet per second. Okay, so it looks like the average velocity slowed a little bit. And this should make sense from the graph, because we're really getting closer to when this object was first falling. Okay, we could see that the object, as soon as it's dropped, is falling at a particular rate, but it's going kind of slow. Over the first half a second, it doesn't really drop that much. But you can see over the last half of a second, okay, this thing went from way up here to way down here. So we know that this object is actually traveling faster later on in its journey. Okay, let's do the last one here. Let's get really, really close to 1. Okay, in other words, we're looking for the average rate of change over the interval from 1 second to 1.1 second. Now, I hope that you can see that really what we've been doing from the very first problem is we've really been calculating the slope of this secant line here. And as this ball moves closer and closer and closer to 1, well, that secant line is slowly becoming a tangent line. And you could probably guess where we're going with this. Okay, so maybe we won't actually do the calculation. We could just kind of look to see that we're at 1.1, and that average rate of change slowed even more to negative 33.73. So back on this screen, the average rate of change, I'll just write this up real quick. We have f of 1.1, whoops, that should be a 1, minus f of 1, all over 1.1 minus 1, which is really 0.1. And we saw that if we perform that calculation, I forgot what it was, negative 33.73 feet per second. Notice, whoops, 0.73. Should be a feet per second. It's kind of sloppy, I apologize. Okay, well, you can probably guess what my next question is going to be. Average rate of change is pretty easy to understand. It's just simply the change in distance divided by the change in time. Well, now I'm interested in what is the speed of this falling object when x equals 1. In other words, what is the slope of that tangent line at 1? Well, by now, if you've watched the previous videos, you should know very well that the slope of that tangent line represents the derivative of my original function. So rather than find that using the limit process by letting this distance go to 0, I now know how to find a derivative. So if I take my initial function, I will rewrite it here, which was 100 minus 16x squared. If I calculate the derivative, dy, in other words, the change in y, the change in distance, divided by the change in x, or the change in time. This is where this notation really makes sense. What is the change in the y variable? Well, what is my y variable? It's a distance. Change in distance divided by change in time equals, okay, well, what's the derivative of 100? It's just 0. And what's the derivative of negative 16x squared? It is, I'm just going to use my power rule here, and this will be negative 32x. So my derivative at any time x, is going to be negative 32x. Okay, well, I'm interested in the derivative specifically when x is 1. So effectively what I want to do is I want to substitute time equals 1 in for x, and we know that my object will be traveling at exactly 32 feet per second when time equals 1 second. There you go. This is my instantaneous rate of change, my instantaneous velocity, compared to these others, which were average rates of change. And really they're calculated the exact same way, but when we go to the instantaneous rate of change, we have to rely on our friend the derivative to make that calculation. I hope that made sense. We'll see you around.